So we've got a couple of my favourite proofs coming up over the next couple of examples. First one is prove that root 2 is irrational. And this is done by contradiction. So what we're going to do first is assume that root 2 is rational and then show that can't be the case. So what we're going to do is suppose that root 2 can be expressed as a fraction. Now, if it's going to be expressed as a fraction, we need to make some stipulations about a and b. So root 2 is a over b, where a and b are integers and a and b have no common factors. In other words, what we've done here is we've made sure that a and b are integers, which they need to if it's going to be an actual fraction. Remember, you're not supposed to have decimals or other fractions on top and bottom of fractions. And saying they've got no common factors means I've cancelled that fraction down. Okay, so let's start with root 2 is a over b. Squaring both sides gives us 2 is equal to a squared divided by b squared. And that gives me that a squared is 2b squared. Now, b is an integer, therefore b squared is an integer. If you multiply it by 2, it must be even. So that tells me that a squared is even. And the only way that that can be true if a is even. If you square an even number, you get an even number. If you square an odd number, you get an odd number. So we can say that a is equal to 2c for some integer c. That means here we can write 2c all squared is equal to 2b squared. So that gives me 4c squared equals 2b squared. And therefore b squared is equal to 2c squared. So b squared is even, which means that b is even. And at that point we have a contradiction. The reason is we said that a and b had no common factors up here, and we've contradicted that. We've shown that a has to be even and b has to be even. So they would have a common factor of 2. And that shows us it doesn't work, and therefore the original statement must be true.